Hello, in this recording we'll be going over rational functions. Our goal is that by the end of this presentation, you'll be able to understand rational functions as ratios of polynomials. You'll be able to find domains and excluded values. You can identify vertical, horizontal, and slant asymptotes, and you can be able to sketch rational functions using the intercepts and the asymptotes, and you'll be able to model real-life quantities with rational functions. A rational function is a quotient of polynomial functions. That means we can write f of x in the form n of x divided by d of x, where both n of x and d of x are polynomials, and d of x is not equal to 0 because division by 0 is undefined. So that leads us to our domain rule. The domain of a rational function includes all real numbers except those that make the denominator 0. Here we're given an example. F of x is equal to 1 over x. So first we find the domain. We see that the denominator is 0 when x is equal to 0, so that means that the domain of f is all real numbers except 0. So this in interval notation will be the interval negative infinity to 0, non-inclusive, union 0 to infinity, non-inclusive. So now we look at the behavior near the excluded value. For our case, that is 0. So as x approaches 0 from the left, we see that f of x will go to negative infinity, so f of x decreases without a bound. Now as x approaches 0 from the right, f of x goes to positive infinity, so f of x increases without a bound. So on the far right, here's the graph of f of x is equal to 1 over x, and we see that the graph approaches 0 from both sides, but never touches it. The line x is equal to a is a vertical asymptote of the graph of f when f of x approaches infinity, or f of x approaches negative infinity as x approaches a from the right or from the left. The line y is equal to b is a horizontal asymptote of the graph of f when f of x approaches b as x approaches infinity or x approaches negative infinity. So now we'll be analyzing the behavior of f of x is equal to 1 over x. So as x approaches 0 from the right hand side, f of x approaches negative infinity. As x approaches 0 from the right hand side, f of x will approach positive infinity. So that means the vertical asymptote for 1 over x is equal to 0. Now as x approaches negative infinity, f of x approaches 0. And as x approaches positive infinity, f of x approaches 0. So that means the horizontal asymptote for f of x is equal to 1 over x is y is equal to 0. And we see that with our function, that the graph will always approach x is equal to 0 and y is equal to 0, but it will never touch it. So here we have some more examples. F of x is equal to 2x plus 1 divided by x plus 1. We see that we have a vertical asymptote of x is equal to negative 1. The graphs approach x equal to negative 1, but never touch it. So now for our horizontal asymptote, we have y is equal to positive 2. Once again, the graphs approach positive 2, but never touch it. Before going over some general rules on how to find vertical and horizontal asymptotes, first we can define n as the degree of the numerator, so the greatest exponent of the polynomial in the numerator. M is equal to the degree of the denominator, so the greatest exponent of the polynomial in the denominator. An will be the leading coefficient of n of x, and bn will be the leading coefficient of d of x. So for our first rule, vertical asymptotes occur at the zeros of the denominator after simplifying. For rule number 2, if the degree of the numerator, n, is less than the degree of the denominator, m, then we will have a horizontal asymptote of y equal to 0. Now if n is equal to m, the horizontal asymptote will be a ratio of the leading coefficients, so y will be equal to an divided by bn. Now for rule number 4, if n is greater than m, there will be no horizontal asymptotes. For example A, we're given the function f of x is equal to 2x squared divided by x squared minus 1. So first we will be comparing the degrees. So since they are equal to each other, we have an exponent of 2 of both the numerator and the denominator. Then we will be comparing the leading coefficients. So the leading coefficient in the numerator, an, is equal to 2. The leading coefficient of the denominator is equal to 1. So that means the horizontal asymptote will be a2 divided by b2, which is equal to 2 divided by 1. So our horizontal asymptote is y is equal to 2. Now for the vertical asymptotes, we stated that they occur at the zeros of the denominator. So we see that our denominator is a difference of squares. So x squared minus 1 can be factored into x plus 1 times x minus 1. Setting each of those portions equal to 0, we get that x is equal to negative 1 and x is equal to 1 for our zeros. So that means we will have two vertical asymptotes at x is equal to negative 1 and at x is equal to 1. Now, for example B, we're given f of x is equal to x squared plus x minus 2 divided by x squared minus x minus 6. So both polynomials in the numerator and the denominator can be factored. So for the top quadratic, we'll have x plus 2 times x minus 1, and for the bottom one, we'll have x minus 3 times x plus 2. So since we have an x plus 2 and we're multiplying in both the numerator and the denominator, we can cancel out those terms. So the simplified portion will be x minus 1 divided by x minus 3, and this will hold for x not equal to positive 3. So since the degrees of the simplified numerator and denominator are equal, then we will compare the leading coefficients. So since we have 1 for the leading coefficient in the numerator and 1 for the leading coefficient in the denominator, our horizontal asymptote will occur at y is equal to 1 divided by 1, which is equal to 1. Now for the vertical asymptote, we set our simplified denominator equal to 0. So x minus 3 equal to 0 implies that x will equal to positive 3. So we will have a vertical asymptote at x is equal to 3. Now holes happen at the cancelled factors. So we saw that before we analyze the horizontal and vertical asymptotes, we canceled out the x plus 2 in both the numerator and the denominator. So that means we will have a hole at x is equal to negative 2. So to solve for y, we can plug in negative 2 into our simplified version. So negative 2 minus 1 divided by negative 2 minus 3 will equal 3 divided by 5. So our hole will happen at the point negative 2, 3 over 5. Here are some guidelines for graphing rational functions. So by definition, we let f of x equal n of x divided by d of x, where both n of x and d of x are polynomials, and d of x is not equal to 0. So first, we simplify f of x. If possible, we list any domain restrictions that are not implied by the simplified function. So that means our values that make d of x equal to 0. And we want to do that because division by 0 is undefined. Next, we find and plot the y-intercept, if any, by evaluating f of 0. Now, we can find the zeros of the numerator, if any, and then plot the corresponding x-intercepts. Now we can find the zeros of the denominator, if any, then sketch the corresponding vertical asymptotes. Now we can find and sketch the horizontal asymptote or slant asymptote. Now we can plot at least one point between and beyond each x-intercept and vertical asymptote. Then we can use smooth curves to complete the graph between and beyond the vertical asymptotes. So test intervals help you determine the signs of a rational function. A rational function can change sign both at its zeros, where n of x is equal to 0, and at its undefined values, where d of x is equal to 0. Some graphing utilities may incorrectly connect branches across vertical asymptotes in connected mode. So switch to dot mode to see the correct behavior as separate points. Here we'll be practicing sketching rational functions. So first we are given the function g of x is equal to 3 divided by x minus 2. So first we want to find our domain restrictions. So that'll be all real numbers except that x is equal to 2. Because plugging in 2 in the denominator, we'll get 2 minus 2, and that'll give us 0. Now for our y-intercept, we plug in x is equal to 0. So for g of 0, we get 3 divided by negative 2. So our y-intercept happens at 0, negative 3 over 2. We have no x-intercepts. Now for our vertical asymptote, we got x is equal to 2 because our vertical asymptotes occur at the zeros of the denominator. For our horizontal asymptote, since the degree of the numerator was less than the degree of the denominator, we will have a horizontal asymptote of y is equal to 0. Now we add some additional points for when we are connecting the dots. So we have g of negative 4 is equal to negative 1/2, and g of 3 is equal to 3. Now using our 0 from the denominator, we have the test interval negative infinity to 2, and we choose a representative x, 0, and we get g of 0 is equal to negative 3 over 2, so that has a negative sign. Using the test interval to the positive infinity, we choose our representative x of 3, and we get g of 3 is equal to 3, which is positive. So now, using our additional points and the representative x's, we can now connect the dots and have our graph. Now for example 4, we have f of x is equal to 2x minus 1 divided by x. So first, for our domain restrictions, we will have all real numbers except at x is equal to 0. For our y-intercept, we have none. And for our x-intercept, we have the point 1/2, 0. For our vertical asymptote, we had x is equal to 0. And for our horizontal asymptote, we are comparing the leading coefficients, 2 and 1, since the degree of both the numerator and the denominator are equal. So 2 divided by 1 is equal to 2, so our horizontal asymptote occurs at y is equal to 2. Now we construct our test interval using our zeros. So we have negative infinity to 0, and we choose a representative x of negative 1. So f of negative 1 is equal to positive 3. Now for 0 to 1/2, we choose representative x of 1/4, which is equal for, once plugging in 1/4, we get negative 2, which is a negative number. Now for our interval 1/2 to positive infinity, we choose 4. So f of 4 is equal to 7/4, which is positive. Now using all the points that we plotted, we can now connect all of them and have our function graphed. Here are some more examples of sketching rational functions. For example 5, we have the function f of x is equal to x divided by x squared minus x minus 2. So first we want to simplify the denominator. So x squared minus x minus 2 can be factored into x plus 1 times x minus 2. For our y-intercept, that'll happen at the origin, 0, 0, since f of 0 is equal to 0. For our vertical asymptotes, we stated those happen at the zeros of the denominator. So setting x plus 1 to equal to 0 will imply x is equal to negative 1, and setting x minus 2 equal to 0 will imply x is equal to positive 2. As for our horizontal asymptote, since the degree of the numerator, 1, is less than the degree of the denominator, 2, we'll have a horizontal asymptote of y is equal to 0. Now constructing test intervals from our zeros, we have negative infinity to negative 1, negative 1 to 0, 0 to 2, and 2 to positive infinity. Choosing some test x values within those intervals, negative 3, negative 1/2, 1, and 3. After plugging in those values into the function, we get f of negative 3 is equal to 3/10, so that is positive. F of negative 1/2 is equal to 2/5, which is positive. F of 1 is equal to negative 1/2, which is negative. And f of 3 is equal to 3/4, which is positive. So now we can plot all of those points and connect them and have an accurate curve. So we see that as x approaches positive and negative infinity, f of x will approach 0. So the graph approaches the horizontal asymptote, y is equal to 0. For example 6, we are given the function f of x is equal to x squared minus 9 divided by x squared minus 2x minus 3. So the numerator is the difference of squares, so x squared minus 9 can be factored into x minus 3 times x plus 3. The denominator, x squared minus 2x minus 3, can be factored into x minus 3 times x plus 1. And we see that we will have a whole at x is equal to 3 because we will be canceling out the term x minus 3 in both the numerator and the denominator. So now our simplified form is x plus 3 divided by x plus 1, and this will hold for x not equal to negative 1. So for our y-intercepts, we plug in x is equal to 0, and we will get 0, 3. For our x-intercept, we will get negative 3, 0, since x plus 3 set equal to 0 gives us x is equal to negative 3. For our vertical asymptote, that occurs at the zeros of the denominator, so we stated x plus 1, so setting that equal to 0, x is equal to negative 1. For our horizontal asymptote, we will be comparing the leading coefficients since the degrees of both the numerator and the denominator are equal. So leading coefficient of 1 divided by leading coefficient of 1 is equal to 1. So now for our whole at x is equal to 3, we need to find the y-coordinate, so plugging in x is equal to 3 in our simplified form, we'll have 3 plus 3 divided by 3 plus 1, so the y-coordinate is equal to 3/2. So we will have a whole at the point 3, 3/2. So now for some additional points, we choose x is equal to negative 4, x is equal to negative 2, and x is equal to positive 2. So f of negative 4 is equal to 1/3, f of negative 2 is equal to negative 1, and f of 2 is equal to 5/3. So after plotting those points and connecting them, we will have a curve. And we see that as x approaches plus or minus infinity, f of x will approach 1. So the graph approaches the horizontal asymptote, y is equal to 1, and there's a hole at the point 3, 3/2. Now, if the degree of the numerator is exactly 1 more than the degree of the denominator, then the graph can have a slant, or oblique asymptote. So we'll go over an example to get the general idea. So we're given the function f of x is equal to x squared minus x divided by x plus 1. So using the long division, we divide x squared minus x divided by x plus 1. So x squared divided by x is equal to x, so multiplying that x back into x plus 1, we get x squared plus x. So now subtracting those two terms, the x squared cancels out, and we're left with negative x minus x, so that is equal to negative 2x. So now negative 2x divided by x is equal to negative 2, and multiplying back that negative 2 into the x plus 1, we get negative 2x minus 2. Now subtracting those terms, we get a remainder of 2. So f of x is equal to x minus 2 plus 2 divided by x plus 1. So as x approaches plus or minus infinity, 2 divided by x plus 1, our remainder, approaches 0. So we'll have a slant asymptote of y is equal to x minus 2. So for a slant asymptote, y is equal to mx plus b, we write f of x is equal to mx plus b plus the remainder divided by the denominator. So as x approaches plus or minus infinity, the remainder term approaches 0. Now we're given another example. F of x is equal to x squared minus x minus 2 divided by x minus 1. So first we factor the numerator. X squared minus x minus 2 is equal to x minus 2 times x plus 1. Now we can divide, and we will be left with x minus 2 divided by x minus 1. So our slant asymptote will be y is equal to x. For the y-intercept, we set x equal to 0, so we'll get the point 0, 2. For the x-intercepts, we let y equal to 0, so x squared minus x minus 2 equal to 0, and those occur at x is equal to 2 and x is equal to negative 1. So we'll have a vertical asymptote at x is equal to 1 from our simplified version. And now we plot some additional points. So we have x is equal to negative 2, x is equal to 1/2, x is equal to 3 over 2, and x is equal to 3. So after plotting all those additional points, the vertical and the horizontal asymptotes, we can now graph our curves. So now one of the applications of rational functions is the cost-benefit model. So we're given the cost C in dollars of removing P% of smokestack pollutants is defined by the model C is equal to 80,000 P divided by 100 minus P, where P is greater than or equal to 0 and less than or equal to 100. So the current law requires 85% removal. The proposed law requires 90% removal. We want to find the additional cost to increase removal from 85% to 90%. So first we plug in the current cost, which is P is equal to 85. So C, or the cost, is equal to 80,000 times 85 divided by 100 minus 85. So we'll have an approximate cost of $453,333. Now the new cost at P is equal to 90, we plug that in, and we'll have an approximate cost of $720,000. So in order to find the additional cost, we just compute the difference. So 720,000 minus 453,333 will give us an approximate cost of $266,667. So to the right is the graph of the model, and we see that rational functions can model rapidly increasing costs as a variable approaches a restricted value. Now another application is finding the minimum area. So our problem states, a rectangular page contains 48 square inches of print. The margins at the top and the bottom of the page are 1 inch each. The margins on each side are 1.5 inches each. So which of the dimensions of the page be to use the least amount of paper? So we see that the printed region is given by x by y, and the total area of the page is given by the length times the width, where the length is defined by x plus 3. So the x is the printed region, plus the 3 from the margins on either side, so 1.5 plus 1.5. So we have x plus 3 for the length. Now for the width, we get y plus 2, where y is the printed region, and the 2 is the sum of the margins on both the top and the bottom, so the 1 inch on the top and then 1 inch on the bottom. So now for the printed area, we can multiply x by y and set it equal to 48, because the page contains 48 square inches of print. Now isolating the y, we'll get y is equal to 48 divided by x. We just divide by x on both sides, and this will hold for x greater than 0. Now for the total page area that we need to minimize, we do length times width, so we'll do x plus 3 times y plus 2. Now we stated y was equal to 48 divided by x, so we can plug that in to our formula. So now area is equal to x plus 3 times 48 divided by x plus 2. Now after we get a common denominator, we'll see that our area is equal to x plus 3 times 48 plus 2x divided by x, and this holds for x is greater than 0. So now we want to find the value of x that minimizes a. So we see that a minimum value, or a minimum, occurs at a turning point. So when the function changes from decreasing to increasing. So after constructing a table, we see that the minimum occurs at x is equal to approximately 8.5. So when x is equal to around 8.5, then y is equal to around 5.6. So plugging in those values, we see that the overall page dimensions will be 8.5 plus 3 is equal to approximately 11.5, and y plus 2 will be equal to approximately 7.6, and we say that our y was equal to 5.6. So 5.6 plus 2 gives us 7.6 inches. So the dimensions that use the least amount of paper are approximately 11.5 inches by 7.6 inches.